Hello everyone and welcome to a new episode of All Things IDA. In today's episode we're gonna be talking about shellcode or importless PE files and how they resolve the needed APIs during runtime without an import directory. Along the way we have to explain how the PEB structure and its related structures work and how they are employed by the shellcode or the importless PE file. The gist of it really is we need to enumerate the loaded DLLs and then find the base and then walk the export directory to find the needed address of functions. With that, let's get started. It is very common to see malware or shellcode being injected into other processes and somehow they figure out how to resolve the needed APIs. It all boils down to parsing, starting with the PEB structure and then parsing the nested structures all the way in order to find the loaded modules. And then once we have the loaded modules as bases, we can start nicely parsing the export directory. So let's illustrate first using WinDbg. And let's pick, for example, Notepad. Let's say here we're suspended in some process. The first thing is there's an extension called PEB. So if we look at the PEB extension, which is explanation mark PEB, it will display some information. And then eventually through the PEB extension, it knows how to follow the PEB structure and nested structures. And then here we have the list of loaded DLLs. Once we have the base of each DLL, we can then go to the PE structure and simply go to the export directory and parse it. We have covered this in previous videos. So for now, our starting point is the PEB. So once we type PEB, the extension will simply parse the related nested structures. So where and how can we retrieve the PEB and how is it really structured along its nested data structures? So if we're using WinDbg, we can access the PEB pointer by simply evaluating the PEB pseudo-register, and we have a list of pseudo-registers supported by WinDbg. So if we search for PEB, we should find it here, address of process environment block and address of thread environment block. We're not much interested in the TEB, although the TEB, if we have it, it has a pointer to the PEB. Now, what is the structure of the PEB? So let's take a look at that. Here, we have an extension as well, or a command in WinDbg called DT to display structures. And we're gonna first just see how the PEB looks like. Say, display type PEB, and this is the layout of a PEB structure. But within the PEB, there are nested structures. In particular, we need to go through the nested structure, the LDR of type PEB LDR data. And we follow this as well. This one has a bunch of links that also takes us to the list of loaded modules. So let's dump that type recursively. So same with the DT, we can pass the -r. And now we have the full picture. Starting from the PEB, we will see the PEB eventually expands. LDR is of type PEB LDR data. And it has a load order module list and memory and so on. These are different doubly linked lists into another structure. So here, let me show you the layout real quick in my notes. So we go from PEB, takes us to PEB LDR data. Now we will have three different doubly linked lists pointing to LDR data table entry. And that structure contains information about the loaded modules, like the base, entry point, and so on. Now, before we move on from WinDbg, just want to show you that we can use the DT command and specify the type and also the address of a concrete structure pointer. So if we use the pseudo-register PEB here, I'm telling WinDbg to display the type of kind underscore PEB pointed by the pseudo-register PEB, which contains the value or the address of the PEB structure. So same story as well. If I say recursively, it should try to find the values from memory and display the fields and their value as pointed by the memory address we specified here. Now let's transition to IDA and see how we can introduce that structure into IDA. Mind you, this structure is not fully documented. So if we go to the MSDN, you can see there is a mention of PEB structure and also PEB LDR data, but it's not the complete structure. So this is PEB, it's not fully complete, and PEB LDR data as well is not fully complete. And these are not supposed to be used by programmers and they're not documented. So let's see how we can get the full definition of those undocumented structures. Now let me show you a trick on how we can use IDA to simply run those tools. So first thing is I'm gonna run IDA with no database, just a temporary database, switch debugger to local Windows debugger. Let's run Notepad as our test program and attach to it. So once I attach to Notepad, in order for us to retrieve the PEB structure using IDA alone, we can use this following trick here in the debugger. So the PEB structure is defined in NTDLL. So we can find NTDLL and simply right click load debug symbols. This will download the PEB file associated with that DLL from the public symbol store, and then it will introduce all the types in the PEB in IDA's local types window. So once we load debug symbols, we should see IDA attempted to download the symbols, and then we have the PDB downloaded here. Now the side effect of that, not only we have a PDB file, we should open the local types window, and now if we search, by the way, here we have 998, so if I type underscore PEB, and here I have the structure. So already this is known to IDA, so we can start applying it. Let's double click and follow it, and here we have a larger definition as opposed to the MSDN online. We don't have everything. So here on MSDN we have just a partial structure and lots of reserved, and these are not really the field names. So a lot of pointers here reserved and so on. But once we get the PDB, look at this now, the PEB structure of size 7C8 hex in that operating system, and it has so many fields that we can look at. Similarly, we should be able to see the PEB LDR data structure as well. So if we follow the LDR data, now we have as well more fields instead of just the bunch of reserved fields and so on. So here in the MSDN PEB LDR data shows us some of the stuff, but here we have a bit more things, not just some of the things. Similarly, the PEB LDR data, as we said here, takes us to LDR data table entry, and also in the local types we should be able to find this. And now this is what we want to reach. So if we look at the LDR data table entry, it should contain the info we need, like DLL base, entry point, size of image. Now that structure as well contains different kind of doubly linked lists that point to the next ones. So once we get the head of the list, we can start walking every entry, go to the inload order link or any other order we want, and we can follow this to the next LDR data table entry, and like this we will be walking from one DLL to the next and retrieving the information we need, like the DLL base in particular. I want to show you a bunch of other ways to get those private data structures as well. So another tool is, I'm going to show you there are a couple ways as well. We can use directly the SymCheck utility from as well the debugging tools from Microsoft. SymCheck exe, we give it a symbol server, and the binary we want to have the PDB downloaded. And as well, we can use resym, a very handy tool by Erwan Grelet. Here, let me show you. So this is the resym tool. It's open source. Thanks for open sourcing. And we can specify, for example, a PDB file to open. And now we can also, outside IDA, explore the structures we need. So for example, here you can type PEB, you can find a PEB. I find that output slightly cleaner than IDA, so I use that tool to recover those structures in the header files I'm going to show you in a second. In resym, once we're happy with the structures we want, we can always save, and then that will create a header file. Now, as of the time of recording this video, resym has some limitations, so we'll have to do some manual cleanup, which I did, and based on the PDB for 32-bit process and 64-bit process, I managed to clean up those two header files. And those two header files contain the TEB and PEB and all the needed stuff. So this is the complete parsable header. We can always also fully import into IDA. I'll show you as well how we can do that. But that structure is very clean. We can include it in our C++ program as we develop shellcode, and we can use it cleanly without hard coding offsets. Now, can we rely on that? Maybe, maybe not. Microsoft tries to maintain compatibility, but there's no guarantee that that layout might not change. So let me show you, if we have those header files on our file system and we want to introduce them to IDA, parse them instead of loading the PDB and from the PDB, if we have them already set, I can run IDA and parse. So we have to do like that. So we're going to go to the compiler. If it wasn't set the proper compiler. But most importantly, we have to select the source parser. And in my case, I selected clang, and that's not going to be enough. So we're going to specify some arguments to clang, depending on which header files we're parsing. So if I'm going to be parsing TEB32, I need to tell the clang parser how to parse it. Now I'm gonna load the header file that's 64-bit structures. I'm gonna pass the following flags: C++ parsing and the target, how big is the pointer size, and so on. That's the arguments we can use for 64-bit header parsing. So here I can simply specify this. Now IDA ships with a bunch of preset switches, but we just have to make sure they're the right switches. And here I'm pasting the right switch for my file. Once I set up that compiler setting and parser, I should be able to simply specify the header file and say file and then load parse header file and specify the header file. If it succeeds, I open the local types, Shift F1, and I have a clean list of structures including the PEB, PEB LDR data, and so on. We could do the same for the 32-bit header file by simply going to the compiler again and changing the switches so the pointer sizes are parsed correctly and so on. Okay, so whether we have the PEB structure from the load symbols and we got them directly or by parsing a header file, doesn't matter. Now let's take a look at the actual layout in memory. Now when it comes to IDA, we don't have a pseudo-register to get the PEB. Instead, we're gonna use an appcall to call into ntdll and retrieve the PEB pointer, and from there we're gonna overlay the PEB structure and follow it and explain to you how it looks like in memory, and then we will write a script to parse it programmatically. If I was using the WinDbg debugger, now I'm using the built-in IDA's debugger, not the WinDbg, but if I was working either with a crash dump or a live process but using the WinDbg debugger, I could have used the PEB pseudo-register to retrieve the PEB location. But otherwise, if we're using a live process and IDA's built-in debugger, I can use an app call to retrieve that. So for example, I can formulate the app call as such. I'm going to show you. This app call, all it does is call into ntdll, which has a helper method called ntdll rtl get current PEB of the following prototype. All it does really is just return the PEB pointer. Let's navigate to that and show it to you. So this is the get current PEB, and you will see that pattern in malware, especially in 64-bit, this one here, that's the implementation. So they get the PEB by accessing GS30 and then offset 60, and they get the PEB pointer. So if you're analyzing shellcode, you'll most definitely see GS30 and this pattern here. Let me run this app call here. So I'm gonna simply run it, and it will return a PEB pointer through the app call object retrieval. And I'm gonna use the special member called _at___ that will give me the pointer of that structure. So let's run that snippet here. That's the output, but I didn't specify a new line. That's the output. So let me clear it and run it again. And this is the PEB structure. So here now we can overlay a PEB structure and start explaining how the PEB looks like. Alright, so this is our PEB. Now let's try to apply the structures. So I'm gonna press Alt Q, and the first structure is PEB. And we have the PEB. Now from the PEB, it has some fields such as being debugged and other stuff that are not in this video, so we're not gonna focus on the other members. What we want is from the PEB, we need to go to the PEB LDR structure, which is in the field called LDR. So if we follow that, now we are at the PEB LDR. So here, if we look again, we have from PEB, we need to go to PEB LDR data, which is the LDR field. It's the PEB.LDR field. So we need now to apply the PEB LDR data here. So do we have it? Yep, here we have it. And now we have the PEB LDR data. And now we have those links in different order. So we have the forward link and backward link. So in the LDR structure, this field points to the head of the list. And this is another form of it, different ordering of that entries that we see, what we point to by those structures. But we have three different linked lists pointing to the same modules list, but in a different order, depending. So one is in the way they were loaded, one is in the memory order list, and one is in the order of initialization. We're gonna keep it simple and just explore the in-load order, so the order of the DLLs as they have been loaded into the process. So now, if we follow one of the links, we said it should take us to LDR data table entry. Let me go to the local types, make sure I have this one automatically synchronized. It is, so we can apply it. Now let's follow the in-load order and apply a PEB LDR data entry. Now, I would like to mention something very important. This structure here, I followed it and I directly applied the LDR data table entry. I could only do that because the inload order links is at the beginning. So that pointer in the LDR data, let's go back to the LDR inload order, that points to the field that is called load order in the LDR here in the LDR data table entry. If we were to follow the in-memory, that link will point to that here at 10. But since I'm looking at the inload link from the PEB LDR, the inloader module list, it happens to be pointing to the beginning of the structure here. That's why I applied LDR data table entry directly at that pointer. But I could have not done the same if I followed that structure, the in-memory order module list, for example. Let's undefine this. If I followed this and I apply an LDR data table entry here, it's not gonna be correct because of the way this pointer points to 10 hex into that structure. So if I really wanted to follow this structure here, let's undefine that, follow it again. I have to go -10 and then apply it. Now it will be a proper layout at the proper start. So for the rest of the video, we're gonna focus only on the inload order module list, and it will always point to the beginning of the LDR data table entry. So as we said, the LDR data table entry now will describe a loaded module, and also it will have links to the next modules, and we might have hundreds of loaded modules. Once we get the head of the list through PEB LDR data and one of the links, and we're gonna pick the inload order. Now every LDR data table entry should link to the next one through that doubly linked list. And then eventually, once the list is exhausted, the forward link will point back to the PEB, to that structure here, to PEB LDR data, and it will point to the first link in the inload order module list. I'll show you what I mean. Once we reach to the end of that list, we will get back to that pointer here, which is at 4D0. So let's follow the first entry. This is the first entry, and if we scroll a bit about the attributes, so we should expect DLL base, entry point, and so on, and even the full name as a Unicode string. So here, this is the first in order, and it is pointing to Notepad. That's the exe. If we follow then the forward link, it should point to another LDR data table entry, and as well, it's going to contain the next entry here. So it's describing now that's the next DLL that was loaded. And also we get its name, get its base, and that's all we want. Once we have the base, it's a regular PE file. We can now parse the exports and so on. And if we keep walking that list, it's going to keep on taking us to subsequent DLLs. So again, let's follow that link. And now it's kernel base. So here we see that whatever we see here is actually in that list. And so as well, some malware go and patch this. So if we look at the attributes of that debug segment, Ctrl S, we can see it's read write. So eventually we can unlink this and make our module invisible. But of course that comes with side effects. We're not gonna talk about that in this video. So if we keep following those links, it's gonna keep advancing us all the way until eventually we go back to the head of the list, as I told you. So there are a lot of DLLs. Now next what I'm gonna do is simply write a script using Appcall retrieval and the way it deserializes so on to make a clean script to parse that programmatically. Before we write the code, let me show you just the gist of that code in a pseudocode form. So we have to start with retrieving the PEB. From the PEB, we'll get the LDR field giving us the PEB LDR data structure. And then now we simply, from the LDR data, we pick any order we want. So we said we're going to focus in the inload order module list. We're going to take the first link, and that now will point to the following structure, as we said. So it's going to take us to LDR data table entry. And now for every current entry, which is of the data entry type, we're going to retrieve the actual LDR data table entry accordingly, and that's the instance of LDR data table entry, and we can now query its attributes, for example, full DLL name or the base and so on. And then from that entry, we're gonna continue with the subsequent links. So here the proper link is called like that, and that is this one. So really what we want is to advance like that. And now we got that entry, and it's gonna keep on advancing until it loops back to the first pointer here, basically, which we can also say pointing back here. And that's the gist of that pseudocode, basically. So we have two steps, and then we reach to the lists, and now we can get entry after entry after entry until we reach back to the head of the list. So let's take a look at the code and how we can implement it. So I prepared the code. I'm gonna explain it in detail and run it. Now let me grab the code and show it to you. And that code now is gonna be targeting one load order as we described, the in-load order module list. Let's go to the live process here. In order for this code to work, since I'm not hard coding any offsets into any structure, although we can rewrite that code and hard code things and not rely on the existence of those local types in IDA. But for now, that script is gonna be using Appcall, and it will be using typed objects and a retrieve method to simplify hard coding offsets. And a prerequisite for that is to have the local types populated with the structures we need to work with Appcall. So I have the PEB and so on introduced, as I said, either through right-click load PDB on anti-DLL or by preparing the header file through the techniques I showed you and parsing them back into the database. So my local types is set up for me to work with Appcall and implement the logic to enumerate the list. So I'm gonna create a new snippet and paste the code. I'm gonna walk through the code. So here, first thing we do is I create an app call to retrieve the current PEB. As I said, now if we're working with a crash dump, we have to simply specify the PEB by hand. So we send a command from the WinDbg CLI in IDA. We type, let's say, R PEB. We get the value of the PEB pseudo-register. We pass it to that script, and now I'm going to explain what we're doing with that script. So I define typed objects. If you're not familiar with that, please check my Appcall videos. And the types I want to use is the PEB type. So I created one, the PEB LDR data type, and also the table entry that will contain the DLL name and base and entry point and so on. Then I want to decide what bitness I'm working on. So am I working with 64-bit binary or 32-bit binary? I introduce a small helper method that simply dereferences a pointer given an address, and I check if it's 64-bit, I use get keyword, and if it's 32 bits, I use get dword. And I also define the pointer size as well because I'm gonna need it. And then if the user did not specify a PEB, I'm gonna retrieve it, and as well I'm using the special attribute of Appcall whenever we retrieve an object. If it's a complex object, not a basic type, then it has a hidden field that is not part of the structure but is introduced by Appcall. So it's the __ at, which means where is that structure in memory. So I get the PEB structure location, and then I use the PEB type to do typed object retrieval. We covered that in the past, and I retrieve a PEB instance. And the PEB instance, I take the head of the list of the in-load order module list, and that's gonna be my stopping condition. So if I'm walking the entries and then the next link takes me back to the head of that list, I break out. So here, as we'll notice, I have a while true, and we'll see the breaking condition. Then what I do, I just simply display some information. Where is the PEB? And then here, once we also ask where is the PEB LDR structure. So Appcall knows how to recursively parse stuff. So since the LDR is nested within the PEB, I get that pointer for free. So I say PEB, since I retrieved that PEB object, I can access the LDR as well, which is an object by itself, and we have more members there. I'm interested only it's in memory location. So I'm also displaying the PEB LDR pointer, and I'm gonna display the head of the list since we're walking it in the load order list. Now I get the first pointer from that list, from that doubly linked list. I get the first pointer to the entry, and that entry is gonna be of the type we discussed here, LDR data table entry. So for every entry, I'm gonna now retrieve the whole entry, and from the whole entry now I have the DLL name, I have the DLL base, and so on. So I take the entry here, I retrieve it. Now either Appcall has some limitation with automatically deserializing certain fields from memory, so I cannot really get the Unicode directly programmatically. Instead, I'm simply going into the Unicode. So full DLL name, if we go back to the structure here and the LDR data table entry, the full DLL name is a Unicode string. If I follow the Unicode string, depending if we are a 64-bit program or 32-bit program, to access the pointer to the Unicode string, in 64-bit program it's +8, and 32-bit program is gonna be +4. So that's what I did here. I simply say, now give me the Unicode string address, and let's advance either 8 or 4 to the actual .buffer field, because IDA doesn't know how to deserialize that correctly. Maybe in the future it will know automatically. It's supposed to. Logically speaking, Appcall should be able to do that, but it's a limitation as of now. But we work around it by simply accessing the field offset directly and retrieving the buffer. So now I have the buffer address. Name EA points to the DLL name location. Then I use the getStrLit contents, pass the buffer address, and tell it I'm retrieving a Unicode string. So I got the DLL name. And then I'm also getting the base. Now when I'm using Appcall, when Appcall retrieves 64-bit value, that field, which is DLL base, which is 64-bit value, 64-bit program, I have to use the .value field. As well, that's a peculiarity of Appcall mechanism. So if we are in 64-bit program, I get that DLL base and then simply say .value to get the 64-bit numeric value. But if it's 32-bit, it's directly accessed through the retrieved entry .dll base, which will be a numeric value. Again, if we look at that structure here, ldr.table entry, the DLL base here is a DQ. That's why when IDA deserializes a 64-bit value, I just have to say DLL base dot value or not if it's 32-bit program. So I get the base, and now I display to the user where is the LDR entry, the index in that list, the DLL base, and the DLL name. It's sufficient for us to get just the DLL base. As a malware writer or shellcode, from the base now they can get what they want. And that's the code pattern we see in real life. And then I simply advance to the next entry. So here, LDR entry, I take that entry, I take the inload order link out of it, and the first field, so here there's an invisible +0. At 0 field, it's the first link, the F link. So I simply take the F link from that entry, LDR entry, and advance. So the next entry I'm gonna be using now is the pointer pointed by the F link here. Here we have the F link, LDR entry. And then I check, before I advance, I simply check for if we are back at the head of the list, and if so, we break out of the loop. Let's run that script and see the output and explain it real quick. So let's run it, and here, look at this. So we got the output. It says, okay, this is your PEB. As we did it manually, it found it correctly. It says the PEB LDR data, it's here, and also your first pointer to start getting the entries is at 4D0. You can see it here, 4D0. That's the F link here. That's the first link. Now I dereference the link in the script, and here where we said we enter the loop. So this is the first entry here. We dereference the F link from the PEB LDR field, and we start loop. So we dereference the first link here, taking us to an actual data entry. And now we have every individual data entry. So this is the first entry. We can see here the address to E60 to E60. And I also parse the base. So here is the base, and that's the name as well because of my script. Same story here. That's the second link, third link, and so on. If we follow it, we have 40 links. And as well here, this is an IDA and the debugger. We can see IDA detected 40. Now IDA does not parse the PEB directly to get the modules list. It's simply using the regular debugging APIs. It receives the DLL load event and it populates that. If it receives DLL unload, it removes an entry. But from a malware perspective, we can always get the PEB using a very simple code snippet. And from there, it's a matter of parsing structures. So basically, if we, again, as a malware writer, all I have to do is simply go to that structure. Let's go to it. And the malware can simply write that code, get the PEB pointer, and start the whole logic from that point onwards. So really, they don't need any dependencies except writing that piece of code. They don't even have to call RTL get current PEB. All they have to do is simply inline that piece of code. They get the PEB pointer, and the rest follows the same logic as per the pseudocode I showed you. Whether you implement it in assembly or C, that's the same logic, or even either Python, as we're walking through that code right now. So that logic here is just universal, doesn't matter what language. What's important is for you to understand how we formulated that and what's the relationship between those structures starting from the PEB. So let me run it again. And here we will see, I'm gonna go to one of the before the last ones, apply the LDR data table entry, points to the next link. And now the next link here, the entry number 40, is going to take me back to the PEB LDR data. Where is that pointer value? So that value eventually takes me back to this pointer here exactly, and we break out. Now, if I wanted to walk another of those lists, remember that we have to account for where it is in that structure here. So in the LDR data table entry, the inload order links is at offset 0, but if I was to walk the in memory, all the pointers are gonna be pointing at +10 displacement. If we're gonna walk into in initialization order links, we'll have to as well, whatever pointer we get is gonna be into 20 hex into that structure. So we simply have to, once we parse the f-link from this, we go -20, for example. If we're working in memory order, we go -10, and this one, it's -0, so in order first link is always also coinciding with the beginning of that structure. Now if I do the same for 32-bit program, so I have a small assembly program which I got rid of its import table by simply clearing out the import table. So here what I did is I took this, I opened here, I went to the import table, and I simply got rid of it. So I just filled it with 0. Now I made an importless PE file. Let's disassemble it. And if I open IDA import, it doesn't have any imports, and that's a 32-bit program. Supposedly this is shellcode and it wants to resolve things. That's what it will do. So let's run it and run the 32-bit version of that code, that enumeration. So here that code doesn't have any imports, but if it had the same pseudocode that we were describing, then it knows how to get what it wants. So first thing is local type window is still empty. Let's go and okay, compiler is good. Depends what we want. I can simply, as we said, load ntdll pdbs or parse the header file. So let me this time parse the header file. So to parse the header file, let's take the 32-bit flags to parse that, go to the compiler, change it to this value here, and let's parse the header file. That's 32-bit value here. Now we parsed it, my local type is properly populated. Now let's take the script and run it. So I'm gonna take that script and run it. That script works both ways, 32 and 64-bit, no problem, because of our conditions here, pointer size and get pointer and so on. So now we are in a 32-bit process here. We can see just 32-bit process. Let's now simply run it. And this should be retrieving PEB as well programmatically. It knows how to deal with the proper Unicode. Let me show you again the Unicode, which is at +4. Let's go to Unicode. Let's see here, Unicode. And the buffer is at +4 as opposed to the 64-bit version. So that script knows how to work both ways. Let's run it. This time here, look what we have. We only have 60 LLs, even though our process doesn't have any imports. So by default, we still get ntdll and potentially current 32 and so on and so on. That's the minimum. User 32 is not loaded. So let's run that. So we should get the same output here. Look at that. We got the main executable with the base, the ntdll. Now, given any base, go back to the PE parsing videos and we can work the exports programmatically. So to recap, we covered the PEB structure, how it is undocumented, and then how we can get the fields using loading the PDB either through the resim tool or through IDA. Once we introduce that into the local types, now we can apply those in the database and we can work the lists manually. And then we hard-coded that logic into a script, and so we can now automatically enumerate those. We can expect the same logic in malware, but it's going to be in assembly syntax. Now that you know the relationship starting from PEB all the way through PEB LDR data and the data table entries, you should now understand how shellcode resolves those APIs even though it doesn't have any imports. Okay, so I hope you found this video useful and I'll see you next time. Thank you.